So this time is going to be acids, bases, and salt equilibrium. So this is everything we've been doing, but it never hurts to hit the high point. So this one may go a little bit quicker, just because I think hopefully you know most of it. Models of acids and bases, again, the basic understanding of what an acid and what a base is the key to this. And it's knowing the two definitions. Now, there is a third definition, but remember, that's no longer going to be asked about. But I do want to just kind of mention that one, and we'll talk about it in a second. So, Arrhenius, acids produce hydrogen ions. Now, before I go any farther, what else could you possibly see instead of hydrogen? Hydronium. I know that that's one of the things that we've kind of had an issue with, of when do you have hydronium and when do you have hydrogen. It honestly all depends upon, do you see a water or not. If you see a water, it turns into hydronium, okay? And if you don't, then it's just going to turn into hydrogen. It's the exact same representation. And then bases produce hydroxide ions. And the question is asked, why is this wrong by today's standards? Do all bases produce hydroxide? No. What's the major exception? NH3. Okay, that is your major exception, because now when we look at the next definition, that is going to make sense. Bronsted-Lowry, acids are proton donors. Now, we talked about why H plus is a proton, because hydrogens have one proton, they have one electron. If it turns into an ion, it has lost that one electron. So the only thing left is the one proton. That's it. So acids are proton donors and bases are proton acceptors. So they're going to gain that hydrogen ion. Now, what does NH, and I'm going to write it up here. You can write it wherever you want to write it. What does NH3 turn into because it's a base? Ammonium, which is NH4. What? Gotta have the plus. Don't forget about that. Okay. So those are the two kind of things. And down there at the bottom, we've mentioned that we're going to get a little bit more in detail to it. Is acids turn into what? The conjugate base. It's going to turn into the opposite. And the conjugates always differ by what thing? One hydrogen ion. So if you notice, the acid has an H plus, and its conjugate base is different by one hydrogen ion. But what do we know about acids? They are donors, which makes sense. It lost it. It got rid of it. And bases are what? Acceptors. Well, what did water turn into? Thought. Accept. Expector. Da 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 da. I don't know that one. So, and then bases turn into the conjugate acid. Those are easy to do. Don't ever mess those up. Okay. Acid in water. Water. Yep. So, if you put an acid in water, it's got to make sense why a hydronium is going to occur, and you're also going to get the anion of that acid. But there's two different ways that acids can dissociate. What are the two ways acids can dissociate? Completely or partially, incompletely, right? And we're going to kind of get into that in just a second. Based on what you see in this one, is it completely or partially? How do you know? Very good. This right here tells me that this is a weak acid. It's very important that you pick up on that. Okay? So if you look at, and again, I don't know how much you've done this, but I wish I had more of these, and that's these particulate representations, because what I want to get to at the very end is showing them the multiple choice tests of the acid base from NIMSY. Have you looked at it? There's like... There are like 10 different pictures with the representations.
Did you text at the workshop last summer?
Again, the particulate representations I feel like is going to be very important in understanding what this is. So if you notice the acid in terms of the pictures, the particles, what happened to it? It lost its hydrogen ion. Well, what did the conjugate acid do? It gained that hydrogen ion, okay? So that's kind of how I want you to look at these things, all right? Next picture. This is, again, the terms that we have to really focus on. What is the difference between strong and weak and concentrated versus dilute? Now, in terms of, every time I hear, or every time I say, what do you think of when you think of an acid? You think of something that's dangerous. You think of something that's going to hurt you. But we know that there are relative terms in that, and that's based upon its pH. But we've been doing this for a long, long time now. What does the pH depend on? The hydrogen ion concentration. Can something be weak but still have a very low pH? Yes. That is dependent upon the concentrated versus the dilute standard. That is the difference. Another prime example. Can a strong acid have a very high pH? Absolutely. If it's very dilute. You can take a bucket of water, drop 1 drop of a strong acid in, and guess what? It's still not going to hurt you even though the strong acid is present because the concentration of the hydrogen ions are very, very low. So strong versus weak and concentrated versus dilute, mainly they're totally different, but they tell you how acids and bases work. So strong and weak is only dependent upon dissociation. Now I want you to write this word down because just in case you see it, I don't want you to always think that it's dissociation. What's another word we can use for dissociation? No. Ionization. I'm not quite sure how their terminology is going to be. I don't know if they use ionization. I don't know if they use dissociation. We just want to make sure that we know both. Yes, sir.
Well, I'd bet they probably pick ionization just because it sounds more intellectual.
It does not sound
Thanks, Alex.
Dissociation.
All right, but weak, we know it's less than 100, but most often when we solve for that percent dissociation, well, I think we did 3 or 4 problems last week, notice they were always less than 5%. Some of them are even less than 1%, but that's just what weak stands for. And then concentrated basically means you have a large number of moles, and weak means you have a small number of moles. That's the difference there. Okay, this is actually another really good picture that I'm glad is here. So if you notice, look at this left picture. What has happened from the reactant to the products in terms of the little molecules? It is 100%, right? Every bit of that has split in 2. But what do you notice in the right one? Parker, there is only 1 right here and 1 right here. So we only had 1 molecule split. So obviously that's going to be less than 5%, right? Okay, so that's the kind of thing that I want you to notice. And if you look at the pictures, you have a very high concentration of ion, another very high concentration of the anion, and then notice HB is HB. There's still quite a bit of it left. Is it exactly 5%?
Yeah, there's 10 and then 1 split, so it's 1 to, so, yeah. No, there's 10.
I don't care.
Yeah, there's 10.
All right, so problem 1, HA plus H2O yields the conjugate acid plus the conjugate base. Again, this is a dissociation of an acid. First of all, just based on the one thing, is it strong or weak? How do you know it's weak? It's at equilibrium, so this is a weak acid. What is the equilibrium constant expression for an acid acting in water? Now, compare the K that is written to the reaction itself. What's different? Very good. Cannon, why does it not have water in it? Water is a liquid. Never write the water in a K expression for anything at all, but especially not for acids, even though that we know all acids and bases have to be mixed with what? Water. If they're not mixed with water, it's not an acid, it's not a base. Can you have solid hydrogen chloride? You sure can. You can buy it in a powder. How do you make the acid? Put it in water, there's your acid. You actually have to buy some of these things in solid powder form. The way you create your acid is mix it with a certain concentration of water, and that gives you your concentration of your acid. If you know how many grams of the acids you can have, just convert it to moles, divide it by the volume, there's your concentration. So you could produce your own acid that way. Okay? Various ways to describe, again, I think that I showed you all this. If it's a strong acid, the Ka is large. Now, what is another way to say large? Greater than 1. So we know that K is equal to products over reactants, right? So how is K large in terms of the math? The numerator is really, really, really big, right? Well, how much numerator do we have in a strong acid at equilibrium? What percentage? 100% product, right? So you're dividing by nothing. So it's got to be super huge.
You're dividing by 0.
That's not fun.
Yeah. So you're dividing by 1.
That's a good point. I've never thought about about it that way. That's a thought to ponder. Okay. Now, position of dissociation or ionization. See, notice what they did. Dissociation and ionization. They use both the words right here. Is far to the right. I hate the words right and left. That is for driving. This is not driving. This is chemistry. Right and left refer to it as products and reactants. That's why whenever you're doing Le Chatelier, don't you ever say shift to the right or shift to the left. You tell them which side you're going to. Very important. Now, what do those squiggly lines mean right there? Approximately. So the concentration of the hydrogen ion is approximately equal to the concentration of what is H, A, and O. Very good. The original concentration of the complete and total acid. And then H plus is much less than the original concentration. Okay? So you mean some reactants? Yeah, it's kind of one of those things. There is a small semblance of reactant simply because of the charge difference. At some point, there will be at least one reactant somewhere in there because of the charge difference.
Didn't you tell us that the strong acids are 95% dissociation?
Yeah, it's like 99.7%.
And above. So there is
Yeah.
some.
Because it has to do with that solubility, 3 grams and 100 milliliters of water.
So that's why it's.
All right, if the equilibrium lies to the right, and again, I hate the directional terms. If it lies to the product, the value of Ka is large or greater than 1. Okay. If the equilibrium constant is to the left, and again, I hate directional terms. We're talking about reactants. Then the value is definitely going to be less than 1. Explain why. All right. Have you ever seen one of these? This really helped them grasp the concept of how to get from one side to the other in terms of what do I use, what formulas. I actually let them use this on the test. I hope that it helped just for an emphatic point of emphasis of knowing if you have a KB and a concentration of a weak base, what's the pH of the solution? Then being able to see, all right, well, if I've got KB and I've got a concentration, how do I get through to OH and then the pH? And so the interesting part about this is that there's 2 ways to do all these problems. You can go left or you can go right, but you're always going to end up the same way. But what we found out is that we really like to use this one right here and
The negative log.
yeah, the negative log. That always makes it easier for us. So that's if you can convert using that, that's always going to be the best way. Okay. This, I don't even know why I even have to show you this. You should know that by now. pH is the negative log of the hydrogen ion concentration. You can use this at any time to solve for the H plus. And this is where I got confused the other day and I messed up because I tried to say something that was wrong. If you need the H plus concentration, use this at any time. But if you need the pH, can you use the concentration at any time? No. When can you only use the exact concentration given?
What's that special word you use?
They give it to you. They give it to you. Problem.
No.
Yeah.
That's scientific notation, totally different.
Yeah, but
Okay, I will talk about that in a minute.
has to do with pH.
Yeah. So if they say, what is the pH of a blah, blah, blah molar solution of this acid? The only time you can take that exact concentration and plug it into this exact formula is if and only if it's a strong acid. Because the concentration of the acid is the concentration of the ion. But if it's weak, what did you have to do? Very good. I'm going to write this. Another step is right here. Ka is equal to x squared over m. Now, since it's Ka, first of all, what does Ka stand for? Equilibrium constant of the acid. Since it's Ka, what is x? It's the concentration of the hydrogen ion. Now, I want to show you where this came from, just in case you forgot. So let's just hypothetically pick HF. Why HF? Very good. That is the one that gets everyone every year. Because it's a halogenic acid. It's got to be strong. No. So, if the concentration is, let's just say, 1 molar, how many ions do you have in solution in the initial? Nothing, right? Okay. So, first of all, let me go in. This is R, this is I, this is C, EX, and then EF. So, we know that this is going to be minus X, plus X, plus X, and then we have 1 minus X, X, and then X. Everybody with me? This is just a Rice table. Well, here's the problem. Do I have any value at equilibrium? No. I sure don't. So, if you don't have anything at equilibrium, you must plug this into K to solve for it. Well, let's have. So, if I have K, did I not have H plus times F minus over HF? Is that true? All right, what were H and F's concentrations? X times X. Now, obviously, we know that translates into what? X squared. But what was the EX for HF? 1 minus X. But if we did this, stop it, Parker. If I did X squared over 1 minus X, in math class, what would you have to do? Quadratic. Never, ever, ever, ever do the quadratic in AP Chemistry. You don't have to. So what can we do with this minus X on bottom? We can neglect that X. Get rid of it. Don't even do it. So that's why that summary equation that I gave you just a second ago of Ka is equal to X squared over M will work. So what is M? The molarity of the acid. That's all you got to do. We've worked this enough that this should rattle off. Real simple. Okay? All right, pH range. If it's equal to 7, it's neutral. Greater than 7, basic. Less than 7, acidic. You should know that. Okay? So, the solution of a... Dang it. The pH of a solution is 8.5. And I can't read the rest of it. Well, I go... What did I say? 8.5. My bad. 5.85. I really think I'm getting dyslexic.
Do that all the time.
I do it all the time.
He's getting mad. He's like, you do that all the time.
What is the H plus for this solution? Now, if you go back to that previous thing, is that in y'all's packet?
Yes.
The previous, where you? All right. Well, here's again is what I said. If you ever need the H plus, you can always solve for it using the pH formula. But the problem is you got to know how to do it. So if I know that the pH is equal to the negative log of the hydrogen ion, I need H plus. Ms. Sullivan, how do you say what was your the terms to use? Okay, perfect. I just want to make sure that we're on this, because I use anti-log. They like, and
They know I'm not a man.
yeah, y'all use what exponentiate. It doesn't matter. Just take the inverse log of the negative pH. Here's where I find problems. Every year that we do this, that little number, that little sign right there messes you up. Okay, you forget to take the negative pH of it. Don't forget, pH is the negative log of the H plus ion. Again, so can somebody punch that in to give me an answer, please? Oh, wow, that was cheap. There it is. Now, my bad. I honestly forgot it was there. 1.4 times 10 to the negative 6 molar. I'm going to throw one at you now. This is totally different. This is not, the answer's not on here. Question. How do you find the hydroxide ion concentration? Come. Okay, subtract the pH from 14 to get what? POH. And then take, you got to exponentiate it. Now, I'm one of those that I embrace KW. Don't give me that. Okay, what is KW equal to? H plus, sorry, I just totally messed this up. Let's try this again. KW is equal to H plus times OH minus. If you will embrace this, it's one step, not two.
More time.
What?
More time?
What do you mean more time?
Means you have more time to do other questions.
Oh yeah. So what I'm saying is it's a direct conversion. All I have to do is divide KW by H plus. Well, I already know what H plus is. What is KW?
What is KW?
What is KW? 1 times 10 to the negative 14. That's all you got to do. So again, this is why I embrace KW. It's because, yes, you're dealing with weird numbers, but the step can save it time. Just throwing that at you. Okay? All right. So calculate the pH of the following solutions. Now, Jonathan, this is what you were asking about. First of all, can I take the concentration that's given and directly plug it into the pH formula?
No.
Yes, you
Yeah,
can,
yeah, you can.
because it tells you this is H plus. Now, this is a terminology that I read. Have you ever heard of Adrian Dingle? Why do y'all laugh every time I say?
haven't really heard it until.
Okay. He is world renowned. He's from New York, and he's kind of like Renee, but I think he's even bigger than her. Yeah, which is impressive. But he calls this factor in front of the x times 10 to the mantissa. Real fancy sounding. So his phrase is anytime the mantissa is 1, then the pH is equal to the positive exponent. All you have to do is just drop the scientific notation, change it to positive.
Renee says something about that, and she doesn't use that term, but she says, look at your, negative exponent and roughly around
Yep.
that number.
Yep. If the mantissa is greater than 1, the pH goes lower. Yep. And again, that just makes sense to me. But it's like I told them, what's the chances of them giving a pH value or a concentration of 1 times 10 to the probably slim to none. Now, on multiple choice, absolutely, because you can't use a calculator and you can't negative log a number in your head. You just can't do it. Parker, you can't do it. Now, the one thing that I do want to bring up, and I don't know if it's in this, but I want to throw this at you, is the pH of this correctly exactly 4? What do we know about pH in significant figures?
I mean, count the decimal places.
Okay, the number of sig figs in the given is the number of decimal places in the pH. So how many sig figs are given? 2, so I need 0, 0. And you look at that, you're saying 4.00, really? But if you go by chemistry law, that's technically the right answer. Okay?
If you put forward, they mark that wrong.
Because that's one thing. There's no way they can assign, because in all 7 questions on the free response, only one part of one question is given a significant figure point, which means if you don't have the correct sig figs, you don't earn the point. There's no way they're going to make it a pH question.
So the 3 rule.
Huh?
The 3 rule.
Always stick with 3 sig figs. So really, if you think about it, that's 3 sig figs. Because the way they do sig figs is plus or minus 1. There's never going to be a problem with less than 2 sig figs, nor more than 4. If they go to 5, then that would be amazing. But 3 is always your cutoff number. Okay? All right, so if we go down, we look at this one. Now, here's the interesting part. First of all, can I get the pH from this exact number? Wine. That's OH minus. But what can I get from this? I can get the POH. So the POH is equal to the negative log of 0.040. Will somebody hit that in the calculator for me?
It's 1.4.
Exactly?
No, 1.39.
Oh, I'm with you. Okay. Yeah, 1.39. And how do I get the pH from that? 14.1 minus 1.39 gives me 12.61. And that's the pH. Okay. Now, both of these examples are strong examples because they give you the exact thing. So then let's move on. Calculate the POH for each of the following solutions. Guys, the only difference here is, can you get the pH directly from from this number right here? No, all you would do is just 14 minus 4. Now, how do I know it's 4? The mantissa is 1, so it's the positive exponent. So which would give me exactly 10. And then you would do the exact same thing for the bottom one. Yeah, you would just take the negative log of the bottom. Okay, everybody good with that one? So that's problem 5. Let everybody write that down on paper real quick. Is all this good because it's real fresh? Okay, all right. The next one, calculate the pH of a solution of 8.5. What is the OH? Did it again, didn't I?
You scroll back up.
The pH of the solution is 5.85. What is the OH minus for the solution? That's where that little octagon thing or the hexagon thingy would help. Is
Go back to the step or problem 3.
so what you could do is there's one of 2 ways. Well, really only. No, you can do it 2 ways. But what I would recommend doing is I would find the POH first, which is 14 minus 8.
5.8.
I hate this number.
You love one.
You used it so many times.
You like 1.8 times 10 negative. 10 negative 2.
All right, what is that? I'm tired of thinking. What is that number? 50 or 15? And then how do you get the POH from that?
That is the POH. You mean the negative log?
How do you get the hydroxide ion concentration? Thank you. I'm running on fumes.
Should have had another chicken biscuit.
I had 2.
What I just say? You should have had another chicken.
Dude, I would be just slumped over in this chair. All right, so what is the anti-log, the reciprocal, the invert? Just give me the answer. Just give me the answer.
7.1 times 2
What?
to the negative 9.
Oh, you're cheating again. Forget that it's on there. All right, good. That matches what our answer says right here. All right. Consider an aqueous solution of 2.0 times 10 to the negative 3rd molar HCl. Now, this is actually a good one. So, based on HCl, strong or weak? Strong acid. So, since it's strong, can I take the exact concentration and plug it in to pH equals negative log of the H plus? Yes, only because it's what? Strong. That's it. Now, is it going to be 3 because that's what the positive exponent is? No, because the mantissa is greater than 1. So notice what happens to the pH. Did it go up? Did it go above or below the 3? A little below. So that's one of the rules to kind of pay attention to. That whatever your exponent is, the pH should be a little less. And it is. It's 2.7. Yes, sir.
You think they'll give us one of those diprotics like we were talking about yesterday?
You know, that's a great question.
They better not.
Because I'm going to be honest with you. All right, so let me just add. Here was the question. Do you remember what the concentration was? Was it 0.2? Yep, it was 0.2 molar. And the question was, what is the pH of H2SO4? So, what? Because you got to remember that sulfuric acid actually can dissociate 2 hydrogen ions. So, this is why I changed it, and I didn't change it for y'all. Yeah, it's a mechanism. So what happens is what it goes through, it goes H2SO4. It dissociates into H plus HSO4 minus, and then HSO4 minus is in equilibrium with H plus SO4 2 minus. So what you had to do was determine the concentration of this and determine the concentration of this, and add them up. Yeah, that's a big stretch. So Chandler, I'm going to be honest. If they give you something like this, applaud, move on. That's a tough one right there. There's no such thing as bonus on an AP exam. No. Well, no. See, the thing about it is it was this one right here would be 0.2 because it was the original concentration, and so if that's 0.2, then this is 0.2. So that means this is 0.2. And so then you would have to do that Ka equals x squared over m.
But you also have to factor in that you already have some H plus in there. Right?
Well, that's why you would add them together at the end. Does that make sense? So what you would end up doing is you would have to find whatever x, excuse me, let me change colors. You would have to find whatever x is because x is equal to h plus, and you would have to add that value to 0.2 and then take the negative log of that number. That's a stretch. That's
They'd have to give you KA too.
yes, and they'd have to give you Ka. And that wasn't even in that problem, was it?
Yeah.
No. Ouch. That was a bad question all the way around.
What are you talking about?
Did you not follow any of that?
Well, I mean, I get what you're saying, but I don't know what problem you're talking about.
This was the test you didn't take.
This is just a, it's not.
Does that have a rise table? Is that how that?
That's how, yeah, let me go back. All right, so weak acid-base problems solve as any other problem, write the balanced equation.
Wait, why did you take the test? Wait, why didn't Chase take the test?
Chase who? He wasn't there 3 days before before.
I was high.
He had his wisdom teeth taken out. That's why he was high.
Yeah, so for those of you who saw me like taking apart.
So write the equilibrium expression using the law of mass action. All this is saying is write the K. Yeah, it was. Solve ice, blah, 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 blah. All right, little hint. You will normally be doing one of two things. Solving for X if you're given Ka or Kb. And again, down there at the little bottom, there's a hint. It says also pH is code for H plus if it's Ka. But you've got to remember that if it's Kb, it's not H plus. What is it? It's OH minus. That's one of those little tricks as well. Or they'll ask you to solve for Ka or Kb by giving you X. Okay, so you're only going to have to do one of those two things. So this is on there, and I'm going to pause the video, and I'm going to let you guys write these down, and then I'm going to talk about them. All right, so notice the top. This is any general reaction for any strong acid and any strong base. Obviously, the strong base is a little more specific because it gives you a strong one. But how many strong bases are there?
8.
There are 8. How many strong acids? There are 6. There's only one strong acid that this won't work for. And which one is it? Sulfuric acid. Why? It's diprotic. Very good. Notice the little purple part that's very important. Never write the water with strong bases. You can, but it makes it more complicated to balance it. Leave the water out of strong bases. Weak acids, what do you notice that differentiates the strong acid from the weak acid? That's it. There's only one thing that differentiates the entire strong acid from the weak acid, and it's that arrow, and it's that important. Okay, weak base, notice it is significantly different, but what's the difference in the weak acid and the weak base association? Okay, now this is something that I've said a lot, and I don't know, well, an acid and a base always produce a salt and a water. Well, what does a salt and a water always produce? An acid and a base. That I don't think has ever clicked with you that reactions are reversible, and that's how it also works. So when you look at the basic salt and the acidic salt, I've given it to you 2 times. I've given you the basic salt of a specific example and then hydrating it to a different thing. So if it's a basic salt, what has to be in solution? It's got to be a hydroxide, right? Well, that's the base. What else does it have to produce? It has to produce an acid, right? Well, HX is your weak acid. Okay? If it's an acidic salt, we've got to have hydronium in solution, and then it's got to be a weak base. Well, NH3 is our weak base. Okay? Now, this is something I've taken out. I've already explained this right here. This is why the Ka thing works the way it does. It's because if you have the Ka of the acetic acid of a 0.1 molar solution, and the Ka is that value, then whenever you set up your rice table, you would get x squared over 0.1 minus x. But what can we do with that x? Neglect it. Get rid of it, because that would put us in the quadratic, and we don't want that. And so if you notice, the interesting part is the pH of this thing was 2.87. And how easy is that math? Multiply the concentration times the Ka and take the square root. That's easy math. Okay? But if you didn't take, if you did the quadratic, notice what the pH was.
2.88.
1/100th of a number off. And think about how much more time and complicated the quadratic was to get 1/100th of a number off.
It could.
Stop, Cannon. Okay. All right, so consider a 0.8 molar aqueous solution of the weak acid HCN with a Ka. And then it says, what is the hydronium ion concentration? Now, here's the deal. First of all, there's a clue and an indicator besides the fact, Jordan, that it says it's weak. It says weak, I get that, but they're probably not going to tell you that it's weak. What's the indicator? It gives you Ka. Why would strong not have a Ka? K is for equilibrium. Strong go to completion. All right? Yes, sir.
If they give you Ka and you just like for some reason forget your strong
Okay,
acids,
that's a good point. What if they give you a Ka for strong? Remember, strong goes to completion. The Ka is going to be greater than 1.
and that's the indicator
Yeah.
that you're strong. But if you just go ahead and solve, like, do the equation with K, would you still get? the
That is a
correct
great
Ka?
question. I would assume you would.
Can we do something like that?
No, because I don't think they'll ever do that to you. I'm fixing to do it, yeah. Okay, so they've given us a concentration and they've given us a Ka. Well, here's the deal. My question is always going to be the first thing. Can I take the exact concentration and plug it in to find the hydronium ion concentration, or find the pH? Only if it's strong. So here's what I need. I need the Ka is equal to x squared over m. But what have they asked me to solve for specifically in the question? Hydronium. What part is hydronium of this formula? It is the x. So x is going to equal the square root of Ka times m. Guys, I'm begging you, on May 4th, show this. Don't just show the numbers and the formula and write down an answer. You've got to prove that you are smart enough to know where this stuff comes from. Not lazy enough to prove that you're lazy.
Can I share something with you?
Go ahead.
You can write this all in one. You can put it into the calculator as one because you're just taking the negative log of that number. So negative log of the square root of Ka times m
I'm impressed.
equals.
I was trying to explain that to you the other day, but you didn't want to hear it.
All right, so bottom line is what I'll show everybody what you did just a second ago. So when we find x is going to be this green number, okay? But let's pretend that this question did not say what is the hydronium ion concentration. Let's pretend that the question was what is the pH. Now, honestly, Jonathan, that's where my math weakness sometimes comes in. What he said, you can actually do this all in one. He said you can take the pH is equal to the negative log of the square root of Ka times m.
That leaves lots of room for error.
No, it doesn't.
That,
It's the same exact thing you're doing.
It does, I'll miss a typo.
well, I mean, it prevents
But the point is mathematically they're equivalent, and you're actually combining it into a step, and that's pretty genius. I'm impressed.
And it prevents rounding, which actually gives you more accurate answer.
This is actually more accurate. He's right.
So every time that I've said like a different answer in class, it's because I did this and not.
I do. I like this. I think that this is an interesting way to look at it.
Booyah!
You
See, now you need to add more arrows in there, so like skipping steps and stuff.
okay?
Like from.
No. Okay. All right. So making your life a little easier again. This is the exact same thing we talked about, but in this point, again, like I said, we can neglect the x. The tricky part is make sure that you understand when we're talking about Ka, x is the H. When we're talking about Kb, x is the OH minus. So if they give you the concentration of a weak base and they give you Kb, can you get the pH directly from those numbers? No. You got to solve for POH first and then convert it to pH again. Okay? Percent dissociation. Now, and I've told you this is real easy. I've been telling you this for 2 years now. What does percent stand for? Part over whole. What does ionization stand for? Turning into an ion. Well, if you think about it, ionization is we're trying to figure out how many ions are now in solution. Well, what ion will be in solution of an acid? Sorry, Jordan. H plus. So what we really need is how many hydrogen ions fell off of HA. Okay, nothing. So there is a little bit of a trick to this. Is the easier way is that H plus is X, which we already know, and HA is the initial concentration that's given. So take X, divide it by the initial concentration, multiply it times 100. Now, one of the problems on the test that you guys had to do was it said the percent dissociation of an acid is 3.5%. What is the pH? Think about that. But the point is, if the percent dissociation is 3.5%, the concentration of the acid, does anybody remember that what it was?
Concentration of H.
Let's just call it 0.5. Okay. Well, here's the point.
It was 0.5.
Was it really?
Yeah.
I'm impressed with myself.
Because you did all the concentrations as 0.5.
Okay. So here's the deal. We know the percent dissociation is part over whole. Well, we know the percent. We know the original concentration. Well, all I'm missing is H plus. Well, they would have to give me Ka, right? Well, Ka is equal to X squared over M. Don't I have Ka? They would have given that to me. I have the concentration, which is 0.5. All I'd have to do is solve for X squared on top. Well, then once I have X, can I plug it into there? Yeah. Or I could just take it right from pH. Okay? So you can work these problems a multitude of ways. You all right over there?
Yeah.
Okay?
Can you just multiply the molarity times association and then take a negative one?
Yeah. All right, so here, matter of fact, here's a question. A solution of 8 molar formic acid, which is that formula, is 0.47% ionized in water. Calculate the Ka value. All right, that's interesting. So we know that Ka is equal to X squared over M. Do we have one of these values? What? We've got 8. Does that make sense? Well, I need X. Since it's Ka, what is X exactly? It's H plus. Well, how do I get H plus from this percent of ionized?
Multiply that times
All right, now, so percent I is equal to H plus over HA. Does that make sense? Now, what do we know about all percentages? Can we use them as they are? No, change them. What is that in real number? 0.0047. So H plus is equal to 0.0047 times 8, right? Which is the original concentration, which is HA. Can somebody run that number for me? 0.0376. Well, that just turned into a real easy problem. So if you understand what the percent sign,
Multiplied by 8.
it is multiplied, yeah, because if you multiply HA by both sides, you'll get H plus. Look at the blue.
I'm looking.
You with me?
Yes.
Okay, does that make sense?
Yes.
Okay. Yes, it is square. Where's Avery? I need her to remind me of that. Don't forget to square it.
Got it. You got it.
So, Cannon, you got an answer? Duh, it's right there in green. Sorry.
I got you.
Well, double check, make sure that is the right answer. It is 1.8 times 10 to the negative 4th. So again, what does this mean? If they ask for Ka, recognize that Ka is that black formula. If they give you percent ionization, recognize that percent ionization is that blue formula. And figure out how to flow those two together. Does that make sense? Okay. Do I need to leave that for just a second?
Yeah.
No? Okay. Calculate the percent ionization. All right, so we know that percent I is equal to H plus over HA. Calculate the percent ionization of formic. Oh, okay. Here's the problem. What do we have so far of the percent ionization formula? We've got the original concentration, which is 4, right? What are we missing? H plus. Well, obviously we're solving for percent I. Well, one thing that they're missing from this problem, they gave it to us in the last problem, is what? They didn't give us Ka. So what was Ka from the original problem?
last problem? No, they didn't give it to us in the last problem.
Well, KA, we solved for it in the last problem.
Oh, did we?
Yeah.
But they gave you the isolation.
That's interesting. All right,
Very interesting.
because the percent ionization will be the same for the, no, it'll be different for different concentrations. That's right. What is the Ka that y'all got? No, the K, remember Ka is the same regardless except for temperature change.
Yeah, it's 1.8.
No, that's the answer, not the square root.
No, well, not 8, 4. No, that shouldn't be there. Sure, it's an alternate version. That's all prime means. Yep. All right, did anybody run that?
I multiplied by 8.
That gummit cannon. Well, we know what the answer is,
Okay, but that means nothing if you don't know how to work it.
but I worked it for you. So we're going to get x. We're going to take that number and we're going to plug it in right here.
Okay, so basically.
We're going to divide it by 4.
Where'd you get the 1 point, why'd you use 1.8?
That was from the last problem. Remember?
Are these like connected?
Kinda. Remember that any acid or any compound has a constant K at a constant temperature.
Oh, it's the
Same
same acid.
acid. Is that the right answer? You got the right answer? Okay. Yes, sir.
This is like a random question, but say on the AP Chem exam, if we're doing something that, like one problem asks about something and we get a number and
Okay.
Don't dumb yourself down.
All right. Calculate the pH of a 1 times 10 to the negative molar solution of calcium hydroxide. This question is a lot easier than you would think. First of all, these are the oxymoron questions. Why?
Wait.
It's a base, and they want the pH. But can I take this exact concentration and use it? Why? It's strong. Very good. So here's the deal. So if I have the POH is equal to the negative log, actually,
Yeah, see, that's why I'm kind of like.
so it's the POH, and I see an issue. The POH is just going to be 3. So the pH
Should be what?
is equal to 14 minus 3. Here's what it is, and I know this is the problem. Calcium hydroxide is CaOH2. It's dibasic, which means it has the ability to dissociate 2 hydroxides.
CBS are all like that.
So that's a pain in the butt. I've never seen one like that before, though.
Seeing mud teeth is, what's that word again?
Whatever.
Yeah, you know that one's got me. Next question. All right, again, the acid-base properties of salt hydrolysis. Salts are not always neutral. Some hydrolyze with water, blah, 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 blah. We've already talked about all this. All right, calculate the pH of a 0.75 molar aqueous solution of NaCN. Now, my first question is this an acid or is this a base? It's a salt. Is it an acidic salt or a basic salt? How do you know it's... Because Na is strong. I want you, y'all have this problem in your paper?
yes, sir.
Try to write the reaction for this basic salt. All right, so salts plus water yields acid and a base. Well, we know we are hydrolyzing this thing, so it's definitely going to have HOH in there. Do you write HOH sometimes? Okay, good. Just making sure I'm not the only one that does that. In equilibrium. Now, since it's a basic salt, what has to be in solution? OH minus. It also made an acid, but it came from a weak acid. What was your weak acid? HCN. What's on the product that's not on the reactant? CN minus. That's it. That's all you had to do. Okay?
So is this
What do you mean by backwards? That's if you don't have that, then that's wrong. You did it backwards. You did an acid plus a base. That's wrong.
Okay, but if you include like the full base and the full acid,
Yes, it's got to be a net ionic. Now, here's the part that you need to be able to make. Yes, sir. You sure?
Wait, that's salt, right?
That is a salt. NaCN.
Salts didn't have a equilibrium. Or like salts were.
You know, that's a great question. Do you have an answer for that one? Let's go with better safe than sorry. Go with equilibrium. You've got me on that one. That is true. They do have a K expression. Because see, the salt itself doesn't.
Now, the salt will have a KSP breakdown. Then, in order to get an accurate acid, you have to apply the percent association then from that individual.
Yeah. I would go with equilibrium, but I really don't have a concrete answer. You got me on that one.
Oh well.
Yes. I know. Give me just a second. Okay. This is it right here, right? This is what they gave you.
yeah, no, yeah.
Yeah.
This is what we just did.
All right. So you'd have to set up a rice table. They tell you that it's 0.75, and so you can set all of this up. It's exactly what we just had. And so the problem is we have all of this, but we have no equilibrium, right? So we would have to plug that into kV. So it would equal x squared over m. Well, we have m, don't we? Do y'all have this on paper?
Yeah, no. The right table was not on the
Y'all can kind of just write this part right here. Now, matter of fact, you guys on the paper, though, in that question, did it give you Ka or Kb? Was it the same number? That doesn't make any sense. No. Honest, I didn't make these PowerPoints. This one's got me a little confused. Because here's what I was thinking.
Oh, church.
But I don't know if they converted it or not.
Why is this
Work it.
side
Next.
far away from you?
No, I want to solve this problem. Someone work that.
It's literally like one right there.
All right, here we go. We can do this one, though.
Well, there's that. But
Wait.
literally the same.
KW equals KB
Times KA.
I knew that. Yeah, that's a popular one, isn't it?
All right, guys, here's the deal with this one. So it says calculate the pH of a 2 molar solution of ammonia. Well, all I did was write the reaction for it. So we've got ammonia plus water yields the hydroxide ion plus the ammonium ion. And they give you Kb, but this is one of those oxymoron questions because they ask you about the pH of a base. So when you solve the Kb expression of x squared over m, you're going to get the hydroxide ion concentration. So once you get that value, what can that lead you into? POH. And then once you get POH, how do you get the pH? Subtract it from 14. So that's kind of where this question would lead you. But first of all, how do I know the pH is above 7? Ammonia is a base. That's how that'll lead you into it, okay? So does anybody have a number for X? You would, okay. All right, so this is equal to 0.006. Now I'm going to just add a page. So I need the POH, which is equal to the negative log of 0.006. Jordan, will you do that for me?
Why wouldn't you just want to?
2.2218. So 2.22.
So 2.22. So 14 minus 2.22 is 11.78, which is, I think, is exactly what it says, isn't it? Okay, well, good.
Why wouldn't you want to switch it over to Ka right away?
Because you can't have a Ka of a base. They specifically.
But you find the pH of a base, so why does that matter?
I don't know.
So
All right, well, if you here. So hang on. They say that KB is equal 1.8 times 10 to the negative what, fifth? So what you're saying is find Ka is equal to Kw over Kb and take whatever this number is and do it equal to x squared over m. Is that what you're saying?
yeah.
But here's my problem with that is I don't know if because this is the concentration of the base, if it relates to the Ka. Do you see what I'm saying? That could work. Give it a shot. And then when you do X, that's going to give you H plus. I would be very leery of doing that because of the fact that the concentration they gave you is the concentration of the base, not an acid.
But you would think since
Figure it out. You got a calculator. Okay. All right, multiple choice. See if you can answer those. How many multiple choice parts are there? All right, which of the following can act as both a Bronsted acid and a Bronsted base? Well, here's the deal. If it's a Bronsted acid, you've got to know the definition. What is the definition?
Proton acceptor.
Proton
Donator.
donor. Okay, and a Bronsted base is a proton acceptor. Now, how many of these have an H that it can donate? Every single one of them have an H that it can donate. But here's the problem. How many of them can accept an H? Only 4 of them. We know what the answer is. We know it's C. Why can C not accept a hydrogen? There's no such thing as, 2 pluses, right? It's not going to accept another one because this one is already, it's negative. It can attract a positive. B is negative. It can attract a positive. E is negative. It can attract a positive. But what do we know about water? What can it do? Very good. It can become hydronium. So that is why it is C. All right, next question. If the acid dissociation constant of the acid dissociation constant Ka for an acid is 8 times 10 to the negative 4th, what percent of the acid has dissociated in a 0.5 molar solution?
I did the work.
Did you do the work? All right, so here's what you would have to... All right, this is actually easy math. We can do this in our head. We know that percent dissociation, percent I is H plus over HA, right? Times 100. Very good. Thank you. So, but we need... Please, Alex. We know that HA is 0.5. We just need the top one. So X is, so I know that I need Ka is equal to X squared over M. Well, X is the square root of 8 times 10 to the negative 4th times 0.5. What is 0.5 times 8? 4. All right, so 4 times 10 to the negative 4th. What is 4 to the negative 4th square rooted? 2 to the negative 2. You seeing how this is head math? So what is 2 times 10 to the negative 2 divided by a half? Be very careful here.
Oh, 4.
It is
Dang it.
4 times 10 to the negative 2. Multiply, no,
By 100.
yeah, multiply by 100, which is 4%.
That's by calculating with my head.
You can do this in your head. I did every bit of that in my head.
Easy? Yeah, you did.
I did do that in my head.
I know, but it's easy the way I do it.
But is that not exactly what you did?
I think you put the same question on here twice.
Did I?
For 5 and 6.
Okay, sorry. As the number of oxygens in an atom, as the number of oxygen atoms increase in any series of oxyacids, such as HXO, HXO2, HXO3, which of the following is generally true? The acid strength varies unpredictably. We've talked about this. The more acids, the blank the acid.
Weaker, stronger,
Stronger. Why?
because there's more.
Remember how we talked about this? The end. The acid strength decreases only if X is a nonmetal. That's wrong. Where'd Parker go? Okay. The acid strength decreases only if X is a metal. Wrong. The acid strength decreases whether X is a metal or a nonmetal. Wrong. The acid strength increases. Yes. Okay. Because we're adding more and more oxygens. That's got to be true. So as the number of oxygen atoms increase, the acid strength increases as well. Wow. H is always bonded to a H is always bonded to an oxygen plus O plus O plus O. And then all the way down here at the bottom we have HOCl. What is the formula for the top one? What is the name of that? Strong or weak? Strong. What's the bottom formula? Hypochlorous acid. Strong or weak? Weak. The more acids, the stronger the more oxygen, stronger it is. Remember, this is kind of like a fulcrum right here. What are we trying to do to make it an acid? Trying to break the H off, right? What's happening up there in the top picture with all those oxygens pulling on that bond? It's breaking it. It's making it weaker and weaker and weaker. So what's happening is, pretend like this is the area of emphasis. That the more we're pulling towards the right, the weaker and weaker that bond's going to get. Well, if we want a strong acid, don't we want H pluses? Well, if we want H pluses, don't we want a weak bond? That's why that bond's got to get real weak. So the more acids, the stronger it is. So Alex, I'm going to have to go. Which of the following is the correct equilibrium expression for the hydrolysis of CO2 minus? So here's the deal. So if you actually wrote the reaction of the hydrolysis, what does the hydrolysis really mean? You're adding water to it. So what are you going to get? Very good. So this is what you're going to have. You're going to have HCO3 minus and hydroxide as the products. And what can we get rid of in terms of a reactant? Get rid of water. So the only thing we have on the bottom is CO2 minus, CO3 2 minus, which has to be B. Okay, does that make sense? That's actually a really good point. And that's the only one it is on the bottom. That's easy. 5, a solution of calcium hypochlorite, which is CaClO2, a common additive in swimming pool water, is basic because of the hydrolysis of the OCl minus ion, basic because calcium hydroxide is weak and insoluble base. That doesn't make any sense. What do we know about CaOH2? It's strong. Neutral if the concentration is kept below 0.1. Acidic, well, that's wrong. Acidic, well, that's wrong too. The only part where I would be left is A and C.
Gas supplied.
Yeah, process elimination, guess. And then what is the H plus concentration of a 0.5 molar HCN at the Ka is? Guys, okay, all this is Ka equals x squared over m. So x is equal to Ka, or excuse me, the square root of Ka times m. And you can kind of go from there. All right, any questions on that? Free response.
So you would just use, yeah.
All right, and that's it.